Okay, so I think it's okay now. So this week we're gonna focus on hydrostatics, and I have 5 practice problems for you guys that I want to cover. But before I start, I want to talk about this one thing, and it's, I guess, pressure and hydrostatics. So if you guys remember Bernoulli's equation, or what was shown during week 1 of class, we get that total energy consists of 3 components. The 3 components being internal energy, kinetic energy, and potential energy. And so the term that's going to be used, you're going to see a lot during this discussion, is that potential energy term, which is rho gh, which also can be written as specific weight times height. But the thing is, like, the definition of that of this equation for Bernoulli's equation is much different than the definition that we're going to be seeing in these practice problems, and I'll explain that as we go along. Once again, for Bernoulli's equation, the higher you are, the more energy you have. The lower you are, the less energy you have, based on gravitational potential energy. All right, let's get started. So here we have this system. You have water flowing through. It looks kind of like a Piot tube, but at point A, that static pressure is recorded, and it goes through the water, through mercury, and through oil. And then we get to gauge B. We're given the pressure at gauge B. It's 87 kilopascals. We want to know what the pressure is at point A. So one thing before I start is I wanted to talk about my worldview, not politically, but in terms of this problem. And it's that, to me, when I look at these problems, I'm either moving up or down through the fluid columns. So that's how I see it. I'm either moving up, or moving down. So here's how I see this problem, and I'll just explain it. So I see it as, I take the pressure that I start at minus the pressure I end at. So I'm going to start at point A. I'm going to move through the fluid to point B. So therefore, what do I mean? So first I move through the water, right? I move through my medium water, and then I move down 5 centimeters. I then enter a new medium, mercury, and then I move through mercury, and I move down 4 centimeters. Then I go across this section, and this section, because I have the same height, or I guess same location in terms of z, there's no pressure change, it's constant pressure throughout that location. Then I move up the mercury by 11 centimeters. Finally, I move up the SA30 oil by 6 centimeters. So that's how I saw it. I always saw it as moving down is negative, moving up is positive. That's how I saw it. And this convention works if we do initial minus final location. Okay, so I have all my terms. I want to solve for PA. But before I do that, let me just quickly clarify some of these specific weight terms. So for water, specific weight is 9,790 newtons per cubic meter. For mercury, it's 133,100 newtons per cubic meter. And usually water and mercury are pretty common. And for SA30, which I think I use this in my BMW, but the specific weight of that fluid, that is 8,720 newtons per cubic meter. So once again, we have PB, we need to find PA. Let's isolate and solve. So PB minus 0.05 meters times specific weight of water. I'm going to combine these two terms, so plus 0.07 meters times specific weight of mercury plus 0.06 meters times specific weight of SA30. Plug in my known values, so I believe it was 87,000 pascals minus 0.05 meters times 9,790 newtons per cubic meter plus 0.07 meters times 133,100 newtons per cubic meter plus 0.06 meters times 8,720 newtons per cubic meter. I have my calculator, let me plug it in and solve. So I get that at location A, my pressure is 96,000.4 kilopascals when I solve this. That's my answer. Any question on that methodology of mine? All right, down, negative, up, positive. That's how I saw it. We're to take my process once again and apply it to the next problem, which is kind of the same. So here I have this contraption, this container, liquid container, and this container has three different columns, and each of these columns have a different liquid within them. Hence why there's different heights associated with them. That being said, once again, different fluids, different heights in these three columns. There is a similarity between each of the columns that at the top part of the fluid column, they're all exposed to the atmosphere. Therefore, atmospheric pressure is applied to the top part of each of these fluids, the surface of these fluids, in contact of air. Okay, so we want to solve for H1, H2. H1 is on the left side of our system, H2 is on the right side of our system. So let's start with the left-hand side. And once again, my convention is initial minus final. I will start at the mercury, and I'll end at the water. So, once again, what do I do? So, I travel through mercury first, and I travel down 8 centimeters. I then move across on the left-hand side, constant pressure. Then I move up by H1. Then finally, I enter the medium water, and I travel up the water by 27 centimeters. And because atmospheric pressure is the same on both sides, it'll cancel out to be 0. I'm not going to solve for H1, so I'm going to move everything over. Okay, then isolate for H1. Divided by specific weight of mercury. I'll plug in their associated values. So 0.08 meters times 100 newtons per cubic meter minus 0.27 meters times 9,790 newtons per cubic meter divided by 133,100 newtons per cubic meter. And this should get me 0.06 meters, which is 6 centimeters. That's the height one for the left column. Okay, I'm not going to move to my right-hand side of the system. Same convention. So P atmosphere of the mercury minus P atmosphere on top of the oil. I think the oil, we're given specific gravity. So usually we work with specific weight. So all specific gravity is it's referring to the specific weight of your current fluid that you're referring to with respect to water. So just saying what is your specific weight, with respect to water or compared to water. Okay, let's go through this problem. So I go move through mercury, I move down 8 centimeters, move across, so no change. Then I move up 5 centimeters. Then I move up again through the oil, and that is H2. These atmospheric pressure terms cancel out, I get 0. Isolating for H2. I get 0.03 meters, once I move everything over, times specific weight of mercury, divided by specific weight of oil, which I can break down to be specific gravity of oil, multiplied by specific weight of water. That's based on the definition of specific gravity. So when I plug it in, H2 is 0.03 meters multiplied by 100 newtons per cubic meter divided by 0.78 times 9,790 newtons per cubic meter. Solving for this, I get 0.523 meters, which means that the height too for the oil is 52.3 centimeters. And that's how I solve for H1, H2 for that problem. Any questions? Okay, yes.
I wouldn't know where to start, like from the initial to find, like for this one, it's a different case. So.
I mean, like, I guess you choose.
Okay.
You know what I'm saying? I just chose mercury because, yes.
Common sense, yeah.
Or not really constant, you can, but yeah, I guess mercury because like I want to isolate the heights because I want one unknown per equation that I'm solving. Yeah, but I could start from water going to mercury or oil to mercury, for example, right? But yeah, as long as I make sure that it's one unknown per like one equation, one unknown, it's solvable. If you did oil to water off the rip, you could not solve that, right? Yes.
What is gamma and how do you find those values?
Oh, so gamma refers to specific weight, and those are given in tables usually. All specific weight refers to is, you saw this here where I said Bernoulli's equation, rho g h. That rings a bell, like for potential energy, right? Or gravitational energy, sorry. That pH term, that's all that gamma is. Gamma is rho times gravity. Yes?
Go from rho to S2 times gamma water.
You mean gamma? Or?
There was in the question you just solved last.
You mean this part here?
Denominator. Yeah.
So I think what you're saying is how do I get the gamma for the oil, right? So specific gravity, that we're given specific gravity refers to the ratio between your current, the current specific weight of your fluid compared to water. So it's just a comparison, it's just a ratio to compare the two. So it says, hey, if you had specific weight, or I am 78% the specific weight of water. That's what that term says. That's why I multiplied it here. Oh, yeah. I just rewrote this equation to be, if that helps. Yeah. And yes, what's up?
So for the first part in this problem, for the sign convention, you have it as negative 0.08 meters because you're saying that the mercury is going down and pushing the water up, and that's why the water height is positive.
I'm saying that when I start at mercury, I move down 8 centimeters. Therefore, I'm moving downwards. I should draw a coordinate system, but given that this is my z-axis, I'm moving downwards. That's why I'm saying negative. Not that anything displaced, which maybe the next method I'll show to you, it makes more sense to you. But this convention, which I personally used when I was in this class, is that when I move down, it's negative. When I move up, it's positive.
But what, like, from the problem tells you it moves up or down? Do you just pick?
I guess the water's like, so water's like chilling here, right? Yeah. So then, like, to me, gravity's pointing downwards, right? It's like, well, if gravity or this is upwards because, well, otherwise the water would be falling upwards if gravity was the other way. But I'm having kind of like existential crisis. But the water is like sitting down here, so like that means gravity's pointing downwards, right? So therefore, the direction the gravity points is usually downwards. That's why I refer to that as negative. And the other direction would be positive.
But is the bottom the same shade as the mercury?
Yes, same shade as mercury.
So isn't the bottom the mercury?
Yeah, it is. So this whole
Is
section.
the lower height always negative because it's pushing the other fluid upwards? Is that the idea?
Oh, sorry?
So since the mercury middle parameter is lower level than that of water and oil, that in
maybe you're saying why like the oil and water sits above the mercury, and that is its density. That's why it's sitting above the mercury.
I'm just confused why, like, for the mercury level, you have it as negative, and for the water level, you have it as positive.
Okay, so once again, I start here, right? I start at mercury, or I start initial minus final, so I start at the red and at the blue. Yeah.
Okay.
Okay, so then I travel down 8 centimeters first. When I travel across here, pressure doesn't change. It's constant pressure, right? So I travel across. Then I move up by H1. So that's why it's positive. I move upwards H1. And the water, I move upwards again by 27 centimeters.
And if you were to switch, like, the blue and the red, it'll be the opposite sides. Got it.
Yes. Makes sense?
Yeah.
Okay. Once again, that's the way I see these kind of problems. Everyone sees it a different way. This next method maybe will make more sense to some of you guys. And let me show that. Okay, so here we have an inverted manometer. So we're curious about the height of the water in this section, and we know the heights of red oil, and we know partially the height of the mercury column. So we're given the pressure difference between point A and point B. So, and it's 97 kilopascals. So one way, if we were to my way, we could start at point B and then move backwards to point A. However, I want to stick to the convention of going from A to B. So therefore, this problem, we're going to look at it as final minus initial. So therefore, we got to change the way we think. When we do final minus initial, moving upwards means you're going to see negative terms, or you'll get negative terms. So what does that mean? So the textbook actually prefers this definition more. Final minus initial is what I'm talking about. And it's because when you move upwards through a fluid column, moving upwards, you're experiencing a decrease in pressure value, you know. At the top surface of like the ocean, it's just atmospheric pressure. Moving downwards through the ocean, you experience more pressure. You know, I think every 10 meters you travel through the ocean, that's an entire atmosphere being added above you. So therefore, moving downwards, you see an increase in pressure, so it's positive. Moving upwards, you see a decrease in pressure, which is negative. So it flips. And I'm going to talk about it as I go through. So once again, final minus initial. Let's start at A. We move upwards through the water. Moving upwards through the water means we're going to experience less pressure as we go to the top. Therefore, it's negative specific weight of the water times H. We're seeing less pressure. Same with oil. We're moving up through the oil. We're seeing negative specific weight of red oil, which I got to convert later using this. Okay. And I move through it 8 centimeters. I travel across, so pressure within like the same horizontal line is constant, so I don't gotta worry about that. Then I move downwards through the mercury. Moving downwards through the mercury means I see an increase in pressure. Therefore, it's positive. Plus specific weight of mercury times 18 centimeters plus H plus 35 centimeters. And this is all equal to the pressure difference that we know. Okay? I'm not gonna isolate for H. So I have my pressure difference here. I'm going to move over my red oil term, and that's going to be specific gravity of the red oil times specific weight of the water, because based on that formula I showed above, times 18 centimeters. I'm going to move the mercury term over, so minus specific weight of the mercury times 0.53 meters. And that's equal to negative specific weight of water times H plus specific weight of mercury times H. I'm going to isolate for H and rearrange the equation one last time to isolate it. Okay. Divided by negative specific weight of water plus specific weight of mercury. Let me substitute these values in. So that pressure difference, I think it was 97 pascals, 1,000 pascals, sorry, plus 0.827 times 9,790 newtons per cubic meter times 18 centimeters minus 133,100 newtons per cubic meter times times 0.53 meters divided by negative 9,790 newtons per cubic meter plus 133,100 newtons per cubic meter. Putting into my calculator, I'm gonna get the following. I get 0.226 meters, which means that the height of the water column next to the location A is 22.6 centimeters. That's the answer for that question. Any questions about either methods? It's just how you want to see the problem. For me, it's the first two problems. That's how I see it. But this method's it's the same thing. It does the same job. Okay. If not, let's move to the other big section for hydrostatics. And it usually refers to, water or some kind of fluid within a dam or reservoir where it's exerting pressure on, or in like a container, and it's exerting pressure on each side of the walls. And we want to be able to determine, given like a certain surface or location within your reservoir or dam, what is the force being experienced, where is it being experienced, etc., along those lines. So in this problem here, we have a gate located down here. Oh. And we want to determine the force being applied on it, as well as the location of the center of pressure, which is where the force would be applied at. So the first thing I want to do is look, I want to define my coordinates first. So for me, here, upwards is Z, along the floor is Y, and into the page is X. Okay. Okay. So looking at this cross section. Okay, looking at this cross section. So we have the surface of the water at the top. One thing to note is that as long as we're in the same height in the water, in like this container, no matter where you are, as long as you're in the same height, that the pressure there is constant along those vertical lines, or horizontal lines, sorry. So something to keep in mind. So we want to figure out what is the height of the column sitting above our the gate, and to determine what is the height of the fluid column above it, we want to know the height above the centroid or center of gravity. That's the value that matters to us. So let me draw the gate one more time here. So our gate, based on the description we're given a height or a base and a width, we can assume that this gate is rectangular. So therefore, for a rectangle, the centroid is at the center. So this gate is 1.2 meters long, and it's on like the slanted portion of our reservoir. Right before that point in the reservoir, there's another section along the diagonal, and that is 1 meter. We also know that the height of the top part of this boot is 4 meters. So what we're missing is we want to know what is this Y value that we're missing, so we can determine the total height of the fluid column sitting above your centroid. One way we can do that is through similar triangles. We know that there's a triangle down here with an angle of 4 degrees. Therefore, through similar triangles, that angle is inherited by that red triangle that I've shown here. We can use trigonometry to figure out y, and we're going to use sine. So sine 40 is opposite over adjacent. Opposite's y. Adjacent is for this schematic, 1 meter plus 1.2 meters divided by 2, because it's the halfway distance for the gate. Therefore, y is equal to 1.6 meters multiplied by sine 40. That would give you 1.028 meters. Therefore, the total fluid column height sitting above the centroid is equal to 4 plus y, which is equal to 5.028 meters. Once again, that's the height of the fluid column sitting above your centroid. The force acting on that gate is equal to, it'd be rho g, height of the fluid column, multiplied by the cross-sectional area. We're gonna simplify it down to be specific weight, and this is oil times HCG times A, which we can break up one more time using specific gravity. Okay. So, solving for the force, plug in the values. I have 0.82 for specific gravity, multiplied by 9,790 newtons per cubic meter for the specific weight of the water, multiplied by 5.028 meters for the height of the fluid column sitting above the centroid, multiplied by the cross-sectional area, which is 1.2 meters, multiplied by 0.8 meters. For all these terms, I get that the total force being applied at the gate is 38.75 kilonewtons of force applied to the gate. So that's the first component of this problem. The second component is determining the location of the center of pressure. So I'm going to change my cross-section. I'm not going to look along the XZ it is plane. I know this doesn't follow the right-hand rule, but this is how I visualize this problem, at least. You know what? How about we define x going this way? That makes sense. Okay. So now we're looking at cross-section XZ, and so let me draw what you would be seeing. So that's the top part of the boot. Then you have the gate here. Then you have the remaining part of the diagonal. So, I mean, it's kind of like EG4 CAD, right? But we have our centroid here. That's the CG term that we were talking about to find the fluid column height above it. Now we're going to solve for center of pressure. And usually center of pressure should be set below your center of gravity. I'm going to look into that just to be sure, though, and then I'll update you guys about that. But while we solve for the force being applied using the CG, the force is applied to CP. That's where the force is being applied to. And the distance between those two is YCP. What is YCP? YCP is equal to negative the second moment of inertia times sine angle divided by the height of fluid column sitting above the centroid times cross-sectional area. Let's start the sine angle term first. So as you see here, our gate is sitting on an incline. That's why that sine angle matters. However, if I were to add the subsection to my system or to my reservoir, if I were trying to figure out the CP for this top surface or this bottom surface, the angle is 0 because there's no inclination. So therefore, that whole term cancels out, and the center of pressure is located at the same place as the centroid for horizontal surfaces. However, for vertical surfaces, that's where you see the maximum distance for this between the CP value and your centroid for the vertical surfaces. That's what the angle is saying, or the sine angle term is referring to. The other thing I want to talk about is the second mode of inertia. So here's our gate. So I believe if I were, okay, it moves probably like this, isn't it? But x or IXX, so draw a line here. That second mode of inertia, that term refers to the ability for a certain cross section to resist bending moment. So if I were to like have, if the plate were to basically move, swing towards me or swing away from me, that term IXX refers to that cross section's ability to resist that motion. That's what those two terms refer to. And this is along the x-axis, I guess. Well, maybe the other way. Okay, so anyways, with this equation, we can solve for YCP. I will provide tables in the recording, like the video. I'll attach it or paste it. But for a rectangular cross section, the second mode of inertia is equal to 1/12 times base times height cubed. And according to our cross section and the picture above or schematic, we're told that the height or along like the diagonal, it was 1.2 meters, and we're told that the width of the gate goes into the page by 0.8 meters. So we have our height on our base as well. So once again, back to the equation. Let's plug it in and get our answer. So negative 1/12 times base, 0.8 meters, times height cubed, 1.2 meters cubed, times sine of 40 for the inclination angle, divided by 5.028 meters. Once again, height of fluid column above your centroid, times cross-sectional area, so 0.8 meters times 1.2 meters. So, what do we get? I get negative 0.0153 meters, which is about 1.53 centimeters away from your centroid. So it's a small value, but it's pretty important because the force is applied to the CP, not the CG. Any questions on my process going through this? Yes.
How do you know which one's base and which one's height?
I believe we fixed the z-axis, so wherever the fluid column is, like with respect to the fluid column. Therefore, because the fluid column, it's the way the fluid is pointing downwards. So, therefore, your base would be perpendicular to that. This would be your base. Your height's along z. All right. Any other questions? Once again, this subsection of the problems is the only reason why ENG 35 is required in this course, I believe. So, just gotta get through it. All right. If not, last problem and we're done. So similar problem, once again, we have a reservoir with water in it, and there's a gate sitting at the bottom, this semicircle gate, and due to the water sitting in the reservoir, it's applying a pressure/force on all the surfaces. The gate experiences that force and it wants to open, right? However, there's a force P being applied at A, holding the gate shut. Otherwise, the gate would just spill out, or the water would spill out. So before we start, I just want to point out some things, which is, obviously the gate has a centroid, which is slightly lower than half the radius, somewhere near like the diameter of the circle, center of the circle, sorry. And then we also have a center pressure term. That's slightly below that as well. And once again, the force acts on the center of pressure. So yes, we have a force. We have the force of the fluid pushing out on the gate. We have force P holding the gate close. But because the gate is sitting on the ground, this floor, we also have reaction forces being applied. So it's something to keep in mind when we go to the problem. Okay. I'm a semi-coordinate system, and let's get started with this problem. So, looking at the first cross section, and this refers to the like surface of the water. I want to figure out where the centroid is. Where's the center of this circle? So, I know that before I get to the gate, there's 5 meters sitting above. 5 meters worth of fluid height sitting above the centroid. To get to the centroid, or how do I find like that remaining value, essentially, is what I'm saying. So, once again, in the table that I'll provide, we know that the centroid of the circle, with respect to the center of the circle, is 4r over 3 pi. That's the distance away from the center of the circle where the centroid is. Okay, so in this context, how do we get, so basically what I gave was this value here, but I want the other side of it. So, how do I get that? Essentially, I'll do radius minus centroid location. That'd give me the remaining distance from the top of the gate to the centroid. And that is 3 meters minus 4 pi over 3 meters. Sorry, I messed it up. So it's 4r 3 pi. So 4 times 3 meters over 3 pi. That'd get me 1.723 meters. I wonder if that's right. I think it's right. Okay. So I have with all my terms, I get the height, fluid column height sitting above my centroid, which is 5 meters plus y, or 5 meters plus 1.723. Oh, that's where it was, 7. That's a 7. Okay. Meters, which gives me 6.727 meters of water sitting height column of water sitting above my centroid. Therefore, the force being experienced by the gate is specific weight of the water times the height, fluid column height above the centroid times cross-sectional area. And because we're working with a semicircle, let me just fill that in, as cross-sectional area being pi over 2 times r squared. Therefore, I have 9,790 newtons per cubic meter times 6.727 meters times pi over 2 times 3 meters squared. Okay, so just plug in values, and that force value would give me 931,000 newtons. Or yeah. So that's the force being applied at the center of pressure, not the centroid. So where is the center of pressure? We gotta go through, or we gotta switch cross-section view. So I see my gate, once again. I need to figure out YCP. So, before we start, moment of inertia, second moment of inertia for a semicircle is (9 pi squared minus 64 divided by 72 pi times r to the power 4. So if this ever shows up, hopefully it's on the equation sheet or in the problem. Okay. Then we're at y. YCP is negative second derivative times sine angle it's a vertical surface, so angle is 90 degrees. Divided by HCG times A. Plug in the values. This simplifies to about 0.11. 0.11 times 3 meters to the power of 4 divided by 6.727 meters times pi over 2, 3 meters squared. Solving this will get me the following. I get negative 0.0937 meters, so about 9.37 centimeters below your centroid. That's where your center of pressure is, and that's where the force is being applied onto. Jumping back to our first cross-sectional view, remember the following. So the force is being applied at the center of pressure location. We have the force that is being used to hold the gate in place. And finally, we have reaction forces at the base. Okay, so there's a lot of things going on for sure. So I want to figure out what what the force required to hold the gate in place is. However, I have some unknowns, my reaction forces. I don't know what my reaction forces are. So there's too many unknowns to deal with. So one thing we can do using statics is we want to calculate the moment required to hold, or required, we have to calculate the moment generated by each force in our schematic. And when we sum all these moments together, it should equal 0. If it's not 0, the gate's either opening due to the fluid pushing out, or folding inwards due to the force being too great. So we want that summation of all the moments to be 0. And we can eliminate the reaction forces by setting our origin of our moment to be at that reaction location. Because then the lever arms, the lever arm terms will be 0. We're to find counterclockwise as positive. So therefore, let's start with the force due to the fluids. So, do right-hand rule. I see that gives me a negative term. So, I get a negative moment, and that is the force from the fluid multiplied by the location from point B to point A. From point B to CP. And that location would be if we take the centroid, so we move upwards by the centroid, and subtract by YCP, because that would get us from point B to point CP. I guess plus, because YCP is negative. But that's how you get to CP. Then, force P, doing right-hand roll, that's a positive moment. Okay? And the distance from point B to point A, where force P is being applied, that's just the radius, so it's 3 meters. And this all equals 0. We have all these terms here. We're just going to isolate for P and solve for that. So force times 4 radius divided by 3 pi plus C, or YCP, divided by R. Substituting these values in, I have 931,000 newtons, I believe, times 4 times 3 meters divided by 3 pi minus 0.0937 meters divided by 3 meters. The total force required to hold the gate shut being applied to point A is 366 kilonewton. That's the force required to hold that gate in place. Any questions?
Just go back down to the final solution.
Is it okay? You want to zoom in?
Yes.
Okay, okay. Anyways, at least up to the point where we solve for YCP, it's relatively the same as any other problem. And then it turns to a statics problem at the very end, but that's just to solve for an unknown force that we want. Otherwise, it's the same process. I personally look at it as switch between different cross sections when I do this problem, but you view it however you want to view it. It's usually the same, I guess, 3 steps where it's height of fluid column above your centroid, followed by distance from your centroid to your center of pressure, or I guess solving for your force, and then distance from center of pressure and centroid. Usually those 3 terms you need for these kind of problems. If not, that's the end of my discussion. Thank you.